For the Module 2 Lesson 1 problem set, we're going to start talking about metric conversions. We use meters in metric to measure distance, and what is really nice about the metric system is it's a base 10 system. So as you move up or down, like many of our regular place values, it's a base 10 system, making it fairly easy to remember. Now, I'll point out you may not be super familiar with the metric system because in America we traditionally use the customary, when talking about distance, we're talking miles, feet, yards, inches, but the rest of the world and the scientific community uses this metric system for the most part. And what I want to kind of point out is, just like place values, what we have here is a kind of scale or a place value chart, if you will. So if I were to have 1 in this area, this is known as a kilometer, okay? You probably have heard of that before. There are 2 others before we get to the meter that have names. It's called hecto and decameter, but they are very infrequently used even in the metric system. Usually you have kilometer and meter as your larger distances. So what's interesting is 1 kilometer is the equivalent of 10 hectometers, 100 decameters, and 1,000 meters. So this 1 kilometer is equal to 1,000 meters. If I had 5 kilometers, it would be 5,000 meters. If I had 8,000 meters, it would be 8 kilometers. Interesting enough, we also have a deci, but we are familiar with centimeters and millimeters. And if I had, say, 1 meter, it would be 10 decimeters or 100 centimeters. If you actually look at a ruler, you'll count 100 centimeters in a meter stick. Okay, so these conversions, I'll point out, so this 1 to 1,000 for kilo to meters, and 1 to 100 for centimeters we'll need as we go forward. So as I mentioned here, kilometers, 1 kilometer is equal to 1,000 meters. We said 7,000 kilometers would, 7 kilometers, would be 7,000 meters. And here, when looking at the meters to centimeters, we knew 1 meter is equal to 100 centimeters, which means something like this. I'll hide this. 80 meters, add 2 zeros, would be the equivalent of 8,000 centimeters. Okay? Hopefully, we'll get used to this and use it quite a bit as we go through our different activities. But as we continue, what we're doing is basically converting, just like we would unbundle or regroup in our standard number form. We're kind of doing the same thing with measurement. We're just adjusting which unit we're using. So the equivalent would be, if I had 3 kilometers and 312 meters, if I wanted to only consider meters, I know that this would be the equivalent of 3,000 kilometers added to 312, giving me an answer of 3,312 meters, okay? In similar sense, if I had 3 meters and 56 centimeters, I know to go to centimeters, this 3 would become 300. 300 plus 56 would be 356 centimeters, okay? Let's look at one more here. So if I had 120 meters, that would be the same thing as add 2 zeros and add 46 at the end here. So 12,046 centimeters. Okay? Like I said, we're going to be using this over and over and over again. Continuing down this page, and you'll kind of plug in different questions, is the same type subtraction problems that we've seen before. The only difference is, instead of it just being 4,000 in this case, it's just 4 kilometers. So we're just kind of interacting with those place values and recognizing their value. So in this case, 4 kilometers equals 4,000 meters. So when I go ahead and subtract 280 from the meters, I know I'm going to need to borrow. I can actually leave that, I'm sorry. 0 and 0 is 0, 10 minus 8 is 2, 9 minus 2 is 7, 3 minus nothing. So we would have 3,720 meters. I could also, just for interest's sake, write 3 kilometers, 720 meters, okay? Same type thing, I would move these meters into centimeters and then do the subtraction problem. Now, interesting, these problems talk about answering the problem in the lowest possible unit. And what they mean by the lowest possible unit is, well, not kilometers, but meters. So, 1 kilometer would be the same thing as 1,000 plus 431, okay? 13 kilometers would be the same thing as 13,000 plus 169. So, and it asked me to add these. In this case, I wouldn't go any further. It asked me to answer it in the smallest unit, so that would be the meters. I could cash in for kilometers, but obviously the guidelines don't ask for that. So the answer would be 14,600 meters. Again, what I want to point out is none of this is that new. Instead of it being written out as 1,431, we're recognizing the value of the label kilometers versus meters. To continue kind of questions similar to this, we have some word problems that essentially all we're going to do is we're going to take the information and recreate the problems. It says use a tape diagram to model each problem. Using a simplifying strategy or an algorithm, write your answer as a statement. So quite a lot of work to do, but we are plenty capable of it. So the length of Carter's driveway is 12 meters, 38 centimeters. His neighbor driveway is 4 meters, 99 centimeters longer. How long is his neighbor's driveway? Now, what's interesting about this tape diagram is I could draw 2, but I don't really need to. I know that I have a certain distance of Carter's. I know if I just add on the additional amount, this will tell me the overall neighbor's driveway distance. So what I'm trying to figure out is if I were to combine these, how much would it be? It tells us how long the neighbor's driveway really is. So I can do a few things. I can combine like place values, which is probably the best bet. So I almost have 2 separate addition problems. I have the 12 plus 4, which would be 16 meters, and I have 38 plus 99. So 8 and 9 is 17, carry the 1. 1 and 9 is 10, plus 3 is 13, carry the 1. 137 centimeters. And technically this answer is not wrong, but I know, unlike the previous problem, this is a situation where I can actually cash this 100 centimeters into meters. So our answer would actually be the neighbor's driveway, if I cashed out this 100 as 1, is 17 meters, 37 centimeters long. This may look confusing. What we're doing here is, since we had an overflow of centimeters and we could cash up, we could exchange them. It's kind of like if I had 100 $1 bills, I could trade that in for one $100 bill. It just is the ability to exchange without changing the value. That's what these problems are getting into. So you have a few other problems similar to this where you'll use your tape diagram and explanations. Let's look at last one more time. It says Jason rode his bike this many fewer meters than Allison. Jason rode this many meters. How many meters did Allison ride? So I know that Jason rode a lesser distance. I also know how far Jason actually rode. He rode 1 kilometer, 850 meters. In this problem, I know that if it says fewer meters, my thought is it's subtraction. But in this case, I'm trying to figure out how much Allison rode. So I could actually transition this into an addition problem. What I would need to do is recognize what is the difference between Allison and Jason. It's 529 meters, okay? So if I add these up, what I get is 1 kilometer, 850 meters, plus 529 meters. 9 and 0 is 9, 5 and 2 is 7, 8 and 5 is 13. In this situation, I know that with 1,000 meters, the simplified way I could listen to that is exchange it into kilometers. So it would actually be Allison rode her bike. I exchange that in 2 kilometers, 379 meters.